introduction. Good evening from my side. My name is Alexander. I'm a PhD student at Graz University of Technology, and today I present my paper where I describe a sensor model to simulate the propagation and also the excitation of lamp waves in lithium-ion pouch cells. And these lithium-ion pouch cells are, the number of lithium-ion pouch cells are, the sampled number increased a lot during the years, for example, assembled in electric vehicles, and we need more monitoring of these pouch cells. And one way to give an additional monitoring is by do a mechanical monitoring approach. And this is done on these lithium-ion pouch cells, which can be seen as plate-like structure. When you put an acoustic transmitter on the cell and then a receiver, and what the transmitter then generates a guided wave inside the pouch cell, and it then travels towards the receiver. And depending on the mechanical properties inside the battery, a certain time of flight can be measured between the transmitter and the receiver. And research already showed that there is a correlation between the state of charge and the time of flight. So the state of charge, when the battery changes the state of charge, also the mechanical parameters changes in the time of flight. So this already is shown, but if you consider a battery like this, the pouch cell, it's a plate-like structure, and the theory to describe the guided wave inside this battery is done by lamp wave theory, and actually there is a complete lack of information which guided wave is used inside this battery, and it's not shown how the inner structure of the battery actually vibrates or moves when it's excited. So in my work, I focus on the fundamental research with respect to this excitation and propagation of such guided lamp waves in lithium-ion batteries. So we came up with the idea to develop a model which then increases the understanding of the excitation and also the propagation of these waves. And what we need for a model is reference measurements, of course. But first, let's have a look at the battery. And pouch cells are used in this work is like this. And when we zoom into the structure, we can see that the cell is not a homogeneous material, but it consists of many single layers. And this stack here, the basic 8-layer stack, is repeated many times to achieve its desired capacity of the battery. And what we do now is we need to assign, for our model, we need to assign material parameters to each of these layers. And these parameters are the Young's modulus or elastic modulus, the density, and the Poisson ratio. And we do this for a fixed state of charge. So we do not change the state of charge. And we do the fundamental research on the excitation of the wave. So we want to do this reference measurements through the excitation of the so-called antisymmetric wave mode S0, which will be excited at 3 kilohertz. The excitation will be done with a so-called electromagnetic acoustic transducer, and as receiver we use accelerometers to pick up the wave. And we want to extract two informations from this reference measurement. First of all, we want to extract the information about this antisymmetric behavior, which characterizes this A0 mode. This will be shown in the next slide. And then, of course, we want to know how fast does this wave actually propagate inside the battery. So for the first property, we want to measure this antisymmetric property. We have a sketch of the measurement setup here. So we have the EMAT on the right side. It excites the wave, and the wave then travels towards the receiver, towards the accelerometers. And these accelerometers measure the out-of-plane acceleration. So this is actually the acceleration pointing perpendicular to the surface. And we then measure the acceleration simultaneously. And when we check the measurements of this, we get the following behavior. So in red, you can see the current pulse, which then excites the battery. And in green and in blue, we see the acceleration on top and on the bottom. And what we see is that they are completely in phase. So when the wave travels from right to left and it arrives at the receiver here, we can see that the wave motion on the top and the bottom is the same at this position at every point in time. So we have no phase shift between the measurement on the top and the bottom. And this is this characteristic is referred to this antisymmetric property of this A0 mode. And so we got this antisymmetric property, and we see that on the top and the bottom, it oscillates in phase. Now we can extract a further information, which is actually then the velocity. And here you can see the actual picture of the measurement setup in the laboratory. Here again, you can see the EMAT with its coil and the magnets. It then induces so-called Lorentz forces, and these forces then drive the acoustic or the guided wave in the battery. And what we do now is we now have two receivers. The first one is positioned 50 millimeters from the AMAT, and the second one is positioned 70 millimeters from the AMAT. So between those two accelerometers, we have an absolute distance of 20 millimeters. And when we now excite the wave, and the wave propagates to the battery, again here from right to left, we of course receive two signals. In red, we can see the signal from the accelerometer at the 50 millimeter position. So we can evaluate its time of flight, let's say at the minimum here. And the wave then travels on, and after a certain time delay, we end up here on the second minimum. And we can then actually, from these two time steps, we can estimate the velocity for our wave. And the estimated velocity for this A0 mode is about 70 meters per second. So with this in mind, we have now this antisymmetric property and also the estimated velocity. We can jump over to our sensor model itself. And the model is set up in Console. It's a 2D model, and it actually includes the AMAT as a transmitter and the layered battery structure. If we zoom in here, so this is the battery, and if we zoom in here, we have all the layers included from the top to the bottom, and the actual width of the battery we use is 10 millimeters. And this setup is equivalent to the measurement setup. So this model is equivalent to the measurement setup. So we use the same excitation current through the coil here, and we use evaluation points, evaluation point 1 to evaluation point 3, which are equivalent to the position of the accelerometers. So we then there and extract also the out of plane acceleration. And what we do now is we perform a parameter sweep for the anode and cathode material. Because if we look in here, we have the copper, we have the aluminum, we have the separator, and we have the pouch foil, which is on the top and the bottom, which wraps around the actual battery. Those numbers for Young's modulus density and Poisson ratios are given, but what is actually not known quite yet is this Young's modulus for the anode and the cathode. So we perform a parameter sweep, and we then achieve following results regarding our two properties. First of all, we said we need the antisymmetric property, and the antisymmetric property in the simulation looks like this. Here in red, we had again our current pulse through the raster coil, and if we now extract the out of plane acceleration on the top and on the bottom after 50 millimeters, we see again in our simulation this nice antisymmetric property. So no time delay when we measure or when we extract the acceleration from top and the bottom at the same distance from the AMAT. Regarding the velocity, we get the following result. We now evaluate the acceleration on the evaluation point 1 and 2. So this is on the top side of the battery. So there is the distance between those points at this 20 millimeters. And what we actually see now in red and in blue again are the out of plane acceleration at the 50 millimeter point and at the 70 millimeter point. And when we extract our time steps or points in time from the red and the blue curve at the minimum, we can actually achieve a propagation velocity of about 71 meters per second. So this is very close to the measured velocity of 96 meters per second. So, and these results were achieved for an Young's modulus for the cutout of 21 megapascals, and the Young's modulus for the cutout of 36 megapascals. And now the nice thing when we have this model is we can now look inside the battery and see how this inner layer, how the inner layer structure of the battery actually is excited. And when we do this, we can extract an animated picture. So on the right here, on the top, you can see the EMAT, and we now, let's only look at the left half. So we push in, this EMAT pushes inside the battery. So the excitation is a pure normal excitation. And when we do this, we are able to excite a wave which propagates now from left to right. But what we see is that all the layers, all the single layers of the battery oscillate in phase. So this wave mode could be a potential candidate for a suitable mechanical monitoring because we see all layers are excited and all the layers actually oscillate in phase. So to conclude my talk, we successfully developed a model of a lithium-ion battery, which allows us to simulate the propagation and the excitation. We used an EMAT as a transmitter and accelerometers as a receiver to characterize the propagating waves, and this was used for the as reference. Then we saw that our simulation results are fit the measurement quite well. And what our model now provides is, of course, a visualization of the wave motion inside the battery, and this greatly improves the understanding of the propagation and how improves the understanding of propagating waves in each layer. So for future work, we now want to do sensitivity analysis with this model regarding mechanical parameters and different excitation frequencies. We want to extend this model to 3D, so we also get the impact of possible wall reflections, and of course investigate cross sensitivities with respect to the temperature or pressure. So with this, I want to thank you for your attention.